Hello everyone, I'm Srija Allam and I'm a cloud security architect at Fortinet. I do cloud security with enterprise, medium, and small customers every day. And given my experience, I wanted to talk more about how systems look secure on whiteboard, but they are broken in production. So, modern applications today are no longer monolithic. We all know because of AI, microservices, Kubernetes, several of these, right? They are all distributed, dynamic, and highly interconnected systems. They are usually built on microservices and APIs. For example, like cloud applications, in my experience, right, they are very ephemeral. Things change, virtual machines come up, they get deleted, they get restarted, etc. So everything is constantly being changed. And these environments, we rely heavily on gateways. Like it could be a web application firewall, it could be a next generation firewall, it could be any of this, gateways that is built and is sitting at the edge. But we also use identity layers when we design an architecture. And sometimes we do segmentation to enforce security. So it could be maybe in a Kubernetes environment, it could be a pod to pod communication, or in a cloud environment, it could be a virtual machine to virtual machine, or application to application in a serverless architecture, right? Could be a Lambda function, anything agent to agent in AI. And that's where we enforce segmentation, right, to secure these environments. But here is the problem I always see, and I really want to explore today, is systems that look secure on whiteboard or in the architecture diagram often fail in production. And the reason behind it is because of, not because of the bugs or in the code, but it's really because of our assumptions. And that's called the whiteboard lie, right? And just a simple agenda here. First, will walk through the assumptions behind what we call the secure design. And the next thing I would like to bring in is the five gaps between what the design architecture is and the reality when we deploy those architectures in the real world or in production. And I have also prepared a small demo with Kubernetes architecture here. And I'm going to show how internal trust can be abused. And finally, we'll just end it with a zero trust points, like how zero trust changes that model. And these five gaps here, what I'm mentioning today, are just from my experience. So there might be things that might exist still, not just these five gaps. So, but these are something that I wanted to show and present to you all, depending again on my experience. Usually, what the illusion of secure design is that when we design systems, everything looks clean and controlled, right? When we have an architecture diagram, everything has a path, it follows a path, it looks controlled. We design gateways at the edge. We always say something is internal. Internal is always secure, in our opinion. So that means we assume that controls are enforced consistently, right at the ingress, right at the egress. But production systems do not usually follow diagrams. What they follow is what is reachable. That means there might exist multiple paths or multiple places where the traffic can go. Or the other thing is that we always check what is where we check that if we have to authorize something, we check if the authorization exists. But we do not check where it is coming from, or we could say who is sending it, right? It could be an attacker who is sending that authorization, imposing the system, but we usually do not check that. So that's the illusion of a secure design. So all of us here might have designed something secure, but we might also have seen something to be failed. Imagine, say, if we are basically running some firmware updates, there might be failures, right? Like during the firmware upgrade, but we designed it to upgrade it continuously, come up, restart in a more secure way. But there might be ways where during the upgrades, the security is not enforced, or it might be flawed, and those few seconds might be enough for an attacker to take control. So the real gap is where attackers are not assuming control because of some breached environment controls, but it's more because of the assumptions that we make. So in this diagram, right, just the perfect architecture example, and again, please bear with me, this is just a simple perfect architecture. This could be an AI system, and of course this is not how simple it's in production because we have several components, but because of this talk I just wanted to keep it simple, so that you're all aligned with what I'm sharing here today. So users, we have users, they use client like a mobile or a laptop, whatever the client is, and the traffic is enforced through a gateway. Again, this gateway could be a Kubernetes API gateway, it could be an MCP tool, it could be an next generation firewall, web application firewall, given or take any router or any of these sitting at the edge. The internal side is where an API is sitting, right? Like it could be an API management tool, an API that is built, and then there is database where the API is retrieving those information from that database. So here API is basically a trusted source or trusted component, whereas the database is an internal component, right? And everything looks secure because it flows through a path, and everything and the controls are applied at the edge. However, if I go to my next slide here, there might be an unintended path, meaning the gateway can be bypassed, the internal service might be bypassed. So the user could be, there are good users and bad users, right? So users might be able to, a bad user might be able to get control of this database and retrieve sensitive data. So there is always an unintended path that exists. So this is not just limited to an unintended path. It could be something where we fail to enforce controls, or we fail to verify where a request is coming from continuously. So that's the reality. And what is the whiteboard like, right? Given, okay, we've seen this, right? So what we assume, it's not just again only with the unintended path that I've shown in the diagram, but there might be where we assume traffic follows intended paths. We assume controls cannot be bypassed. We always assume internal is safe and internal equals trusted. And also, when we design an architecture, we start with something small and we scale it eventually. So and we assume that scale doesn't introduce risk sometimes, or we overlook how scale might introduce security flaws. So these are all, again, all of these controls of paths are usually not guaranteed, and they are simply design assumptions. Now, what I found is that every architecture usually relies on assumptions, like all traffic again goes through the gateway or internal systems. And just I want to reiterate is that attackers don't break systems, but they break assumptions, right? And once this assumption fails, the entire trust model is collapsed. That means the breach happens, and then the architecture can be controlled, right? And gaps, right, but there are few gaps, like I mentioned, the difference between the reality and the actual architecture, when we move it into production, is that identity is validated once at the edge. We don't check it continuously once it's internal. So we are only doing it once at the edge. And most of the times, there might be tokens that we generate. Either it could be an API token, or it could be a username password, it could be a service account password that we generate. And then we reuse these across multiple contexts. And that's a problem, because once a token or a generation is compromised, that means an attacker can get hold of the entire system where those are being used. Um, and also the context thing, which we are usually, the tokens are not tied to a workload identity or context, but this is something which we again fall back, right? Like these are not context based tokens. And we also allow identity to be used across multiple paths. So there might be again multiple ways of communication or traffic flow to a certain database, but we might enforce security across one, and we assume that the security can be reused from one path to another, but not really. That again is an attack surface. And authentication will tell us who, but we usually do not verify if it's coming from a certain source or where is the source being originated. So if someone will assume their role as a certain identified or trusted boundary, that means the system will allow it. So usually what we are not seeing here is we are not cryptographically verifying where the request is coming from or the identity is coming from which context. So that's one of the gap. And the second gap is that imagine in a Kubernetes environment, again, here, there are multiple paths, right? One is the traffic can be sent through an ingress, the traffic can be flowed to a cluster IP, or there also exists pod to pod communication. And if we apply security on one path, one intended path, it doesn't apply to all the paths because, again, multiple paths exist beyond these diagrams, given this microservice, how to get to this microservice. And if a path exists, it becomes an attack path. So this dotted lines, maybe we think of this dotted line on a diagram, right? There may be a solid line that is showing a communication path. There are also dotted lines, and we usually assume some security controls. It's the same over the line, a straight line and also a dotted line, but actually not. So we need to make sure that all of the communications are secured irrespective of how they're configured, right? So if a bad path exists, again, it becomes an attack path, and that's something which we need to secure. The next thing is the controls enforcement. Usually security is as often applied only at the gateway. Like I mentioned, right, web application firewall is a great example where we enforce profiles or protection profiles at the entry. And then once the traffic leaves the gateway, which is internal only, we might not be checking where that traffic or the source of the traffic continuously, or we are not applying authentication continuously. So security is applied only at entry points. And sometimes, again, in this web application firewall example, right, the backend might be directly reachable. That means someone can bypass this WAF and then get access to that database in the backend. That's because of not because like and this again, this doesn't exist everywhere. We do lock down the backend to only listen or to only enable forward the traffic from the front end, which is the web application firewall. But sometimes we again fail because there are multiple paths that exist. So the other thing is that if traffic bypasses the gateway, we also cannot implement the controls because we apply the controls at the web application firewall level. But what if someone is bypassing the gateway? That means we do not have anything enforced at the destination level, which in this case is a database. We are just allowing that to be forwarded. So we are basically opening up an attack surface again. So security becomes path dependent in this case instead of system wide. So that's something which we need to keep in mind when we are designing an architecture. The next thing is scale breaks security. This is another thing, given our AI or the world has taken a turn, right? And given the cloud applications, everything is changing, everything grows in time. Very scalable architectures in cloud, for example, because that's where my most day to day is. What I see is that we start with something small. We solve a problem for something small, and then eventually we increase this to scale. So and we assume the security that we apply at a small part of this architecture will also apply to this greater scaled architecture. But that might not be true because again, whatever the security that applies to a simple virtual machine we may not be able to apply when that virtual machine is part of the huge bigger context or a huge landing architecture. So controls do not scale with infrastructure. That means we cannot overlook controls when we scale the architecture, and we also need to take into consideration that as we scale, we also need to scale the security and apply controls. And one more problem is that when we start with an architecture, we design something small, the security works great, but as we grow, there might be places where the visibility is out of control. of course, there are so many tools like clouds, the posture management, cloud security posture management tools, or it could be some other posture management tools. But visibility in cloud environments is really hard, or even in Kubernetes, where these are very ephemeral, right? The pods get created, deleted, the visibility decreases as systems grow. So security is not consistently applied at scale. So we need to keep in mind that we design security for a huge, bigger picture than just concentrating on that small problem solving architecture that we start with. The next thing is the humans gap. Humans break everything, which is true because in an IBM study, interesting fact is that 95% of the attacks or breaches happen because of humans' decision. Human decision is basically, do we have to click a link or not? And we end up, and most of the times, humans, make a decision. So the study shows that 95% of attacks are based on humans. The breaches happen because of humans' decisions, I mean. And if we could avoid that somehow, right, 19 out of 20 breaches can be avoided. So what happens again here is that sometimes temporary access becomes permanent. And sometimes we are troubleshooting, debugging a system failure or system is down. And over time, there is a permission sprawl. So no one will go back and then clear out those permissions. Or sometimes we just leave it because we can come back and maybe reuse it in 2 weeks or 3 weeks and we forget, right? So there is a privilege creep there, which increases over time. And actually, I just wanted to share an example here is that in one of my jobs, this is a simple example again. I was part of a team, and then I moved to a different team. I was part of the distribution list, email distribution list, but I was never removed from the distribution list even after I moved, right, like to a different team. So 2 years into the new team, we still was seeing the emails from the previous team. So this is just a simple example of again how this privilege creep happens and how permission sprawl could grow over time. So it's not just about employees changing the teams, but also employees moving from one job to another, and sometimes misconfiguration, again temporary access, all of this become permanent because of the again debug paths, troubleshooting, etc. So these small changes will accumulate over time into significant exposure. So when we design the architecture again, we do not assume how humans might break everything. So this is another gap that we can think about. All right. So I prepared a very small demo here, and hopefully the demo can be completed. Again, this is no way related to how production systems are, but this is to show how a trust can be abused in a way, right? And this could apply or scale to a bigger architecture, or it could be in an AI system, or it could be an on-premise application that is sitting, or a data center, wherever your application is in the cloud, etc. So the demo setup is this way, where I have users, I have a client, which is my laptop, and then there is a gateway. This is a Kubernetes gateway, and everything is running in a Kubernetes architecture. So I have a pod for a gateway, and this is exposed through a deployment. And then I have a service A and service B. Here, service A is a trusted service. That means the traffic can be sent from the gateway through a service to service A, and service B is an internal only service. Again, stressing out here is internal only service. That means service A can only reach to service B, but nothing else. So if a user wants to access service B, it has to flow from gateway to service A to service B. However, the unintended path that I was mentioning earlier, users might be able to access service B because of that breaking of trust. So let's go back, and I'm gonna show my slide here. Let me get these terminals up. So I prepared again this demo already. So if I do kubectl get pods, like I mentioned, there is a gateway, there is a service A, there is a service B, right? Service B is trusted or internal only service, service A is trusted service, and gateway is at the sitting at the edge, and we are exposing all of this through a deployment here. So I'm just gonna do some port forwarding here to that service gateway on port 8080. So if I start here, it is listening on port 8080. Everything gets forwarded to that gateway. Now, on my right side, right, I'm just gonna run an API call here. So if I'm running an API call here, and this API, by the way, is protected with some kind of authentication, in this case, a bearer token, right? So what my system expects, or a gateway expects, is that if I make an API call without that authentication header, it's going to forward that traffic. But if I add that authentication header, that means it's going to allow the traffic to go to that backend API, and it will retrieve the information from my database, right? So if I run this, of course, I'm an error unauthorized, and we also can see that there was this handling connection for 8080, and it's an unauthorized again. But if I actually run over with an authorization header and it says bearer valid token, that means I should be allowed. So I can see some sensitive data, and then it says internal data. So I'm able to retrieve that secret here. Now, imagine this is great, right? We have authentication headers, but somehow let me do this foothold and then say service A is compromised, meaning I was able to compromise the gateway and I got into service A. No, so I'm going to run into this kubectl, run this command to get into the service A pod. So if you see here, deployment service a.sh, this is a command to get into to log into the pod, right? And I'm at the pod level here. Now, if I run again, and let me bring my API call here. So if I run to service B, because only service B expects that it can see the traffic from service A, right? And I'm an attacker now. I got hold of the service A pod and I retrieve the data. I see error forbidden. This looks great. This is exactly how it's designed. That if we do not supply authentication header here, it breaks at the gateway level. But at the same time, service B is only allowed to receive the traffic from service A. So it's seeing that it's not us. The service A is the traffic doesn't come from service A, so it's giving us that error forbidden. Now let me say I, as an attacker, run this service X service name. This is a header that I'm using to say impersonate as service A, right? And then retrieve the data from B, then I'm getting that internal data again. So I'm able to retrieve that data. So I actually didn't exploit any vulnerability here, but I'm literally breaking the trust. So service B is allowed to receive the traffic from service A, and that's what I impersonated, and I got access. Imagine how, if these service Bs are multiple microservices with having sensitive data, and if you assume your request coming from a certain place, that means we can break the trust, right? So what I'm seeing here is I am not verifying the context. I'm only verifying what it looks like or where it's coming from, but I'm not checking, the service B is not checking who it is actually coming from. So we are not cryptographically verifying if the request is actually coming from service A, or if someone is impersonating service A, right? So that is the problem. That means, like, again, it looked secure on whiteboard in this diagram architecture. If I didn't have this dotted line here, everything looks great. Like, there's a gateway, service A, service B, A to B communication goes through the gateway. But what I did is I broke that trust, and then I compromised service A, and I was able to get to service B. And service B didn't verify if the request is coming from the service A gateway to service B, or if someone is directly impersonating to be a service A and sending the traffic to service B. Now, just to reiterate, right, the gateway enforced authentication, the backend enforced internal only access works great. Both controls were working as designed, because we did see a forbidden when we make that API call from service A. But we access the backend through a different path. We said the header, the valid trust signal that we used, we impersonated to be a service A, and it worked. We were able to get that data. Now, how do we solve this problem, right? Like, we can see this on the NIST blogs or NIST white papers that they mention about zero trust. So, zero trust is where the real meaning is that verify every request that is coming. And we also make sure we bind that to a context. So, we are also checking where the request is coming from, who it's coming from. So, there needs to be an identification of where the request is actually originating. And we move from verify but trust, but we are like no implicit trust, right? We are basically checking every request that is coming in. We are authenticating every request that's coming in, and also east to west segmentation or east west inspection is also highly important when we implement zero trust. So zero trust is the way to go in order to overcome these kind of challenges. It's a lot to implement in production, but once we have a real baseline, then we can improvise over time, and we can get that zero trust based architectures. So what I want to say is that security that survives reality, right? Like, so identity is always important than network. Like, we can do, again, I can mention in case of Kubernetes, for example, we can do mtls, or we can create service accounts, and there needs to be a context based workload identity, and we are not just relying on ips or headers, right? So we do need to make sure that we understand that mtls based, or we do that workload identity in order to overcome these kind of trust based challenges. And every hop has to be verified. So we don't limit the controls just at the edge level or the entry point, but we are authenticating and authorizing every service, as it also the traffic flows through internal side, right? So any internal to internal request, pod to pod communication, or in AI, agent to agent communication has to be authenticated and authorized. The next thing is the path based security, right? We need to apply those controls, and again, we need to verify those controls if the controls exist as security in every path that exists, or every path that we can reach this backend destination. Whatever we would like to protect, right? Sensitive data. We need to make sure that every path is controlled, and controls are applied. And the next thing is the east west inspection, right? So if we have agent to agent inspection that we need to do, like, or virtual machine to virtual machine inspection, application to application inspection, we also need to inspect the traffic. So that's again a way to enforce policies and get that zero trust. Because again, just like we've seen, if an attacker gets hold of that assumption and then gets into the system, internal system, that means they can collapse the entire system, because they can get access to all of these internal services in stealth mode. And we can eliminate the implicit trust. So in my demo, if I go back, we are relying on some headers, we are relying on dns, because we are in Kubernetes, service A can access service B. So we are basically relying on that implicit trust, and we are also implying on working on trusted services that needs to be changed. So we are not trusting anything, even if it's the internal traffic, internal only traffic, or outbound, inbound, external traffic. We are not just trusting blindly, but we are basically eliminating that implicit trust. Again, goes back to my point of where we need to authenticate and authorize every request that's coming in. We can assume breach, like we assume breach when we design, right? Like, we design to limit blast radius. If there is a breach, then we need to also think how much is the blast radius, what could the impact of this attack be, what could be the length of this attack be. And then we also need to make sure we prevent lateral movement. So in my case, again, in the demo, again, if we get to access service A, if service A is hacked, and somebody was able to access service A, the service B should not be reachable directly, right? Or if this service C, D, or several other services, we need to prevent the lateral movement, and so that we can reduce the blast radius. So what I want to conclude is that security is not usually what we design on the architecture again, but we need to think of what we enforce continuously, how we improvise, how we can do it at scale, and also how we can enforce it when systems change, or this ephemeral systems get deleted, added, etc., and also how we can limit to human decisions, or how we can decrease when humans as make bad decisions. Thank you so much for watching, and have a nice day.